Okay, basically, integrals are the opposite of a derivative. In mathematics, an integral is used to calculate areas, volumes, and their generalizations. Integration is the process of computing an integral and is one of the two fundamental operations of calculus, the other being differentiation. Okay, this is basically the integration notation where b represents the end, a represents the start, f of x is the expression, and d of x is the differential. Okay, the first thing you want to do is do the power rule, but in reverse. So basically, you increase the power by 1 and divide by the new power. But don't forget to add the constant of integration, which is basically just plus c. You can take the derivative of the antidifferentiations and get the original function. Apply.
Linearity.
Integration is a linear operator, which means that the integral of a sum is the sum of the integrals, and the coefficient of each term can be factored out. And you can see the notation here.
Consider the integral below. Unlike the integration process before, we now have bounds to evaluate it. For example, the integral from 2 to 3 of x squared dx. Use the fundamental theorem of calculus. Um, you would just integrate that x squared, and that gets you x cubed over 3, and then you plug in 3, and then you subtract it. Um, subtract the function from evaluating it at 2, and that gets you 19 over 3. All right. This first example is question 17. An object is moving in a straight line along the x-axis. The net force F of x exerted on the object as a function of time, t, is shown on the graph. Which of the following could be the momentum of p as of the object as a function of t? So what we know is this force. We know what the force is based off this graph. Force is equal to mass times acceleration. So the mass can never be negative because then it wouldn't be an object. So the acceleration has to, so it's positive. And since the f of x and the graph that we see here, the value of the function is always going to be positive. So this acceleration has to be positive. So what we can do from that is the integral of a in respect to time, we know that that is equal to the velocity. So if the acceleration is always positive, then that velocity is always going to be positive and it's going to be increasing as well. So we know that the velocity is positive and increasing. So how can we relate this to momentum? Because that's what the question's asking for us. Well, momentum is equal to mass times velocity. We know that this mass is always going to be positive. So we know that this momentum has to be either positive or increasing throughout the whole graph. And the only graph that shows that is graph E. Because graph D would be if the acceleration was negative, but the acceleration is positive, so that one can't be right. Graph C is wrong because it has the acceleration changing, because the velocity would be increasing and then decreasing as it goes down along that graph. And then A and B are just simply um, the f of x by f of x respect to t function, but simply flipped for B. So here's question 18. A car is traveling along a straight level road when it runs out of gas at time t equals 0. From this time on, the net force on the car is a resistive force of negative kV, where v is velocity and k is a constant. Which of the following pairs of graphs best represent the speed v and position x of the car as functions of time after t equals 0? So what we have here is that we know that there's going to be a resistive force, and force is equal to mass times acceleration. So we know that this acceleration is going to be negative. Now this acceleration is based off k and velocity, essentially. This k is a constant, so that's not really going to change. So we can treat that k almost as if it's just k equals 1. So it's really just negative v. So if you were to integrate or integrate that acceleration to find that velocity of how much it will or like the velocity as it's changing, it's going to become a, it's going to be a very, it's going to start sloping down quickly because you're going to have that high velocity at the beginning of the time. You're going to have that high velocity because of this right here, because this velocity is pushing this acceleration down further. But as it slows down, the acceleration is going to become slower, and then that velocity is going to start to sort of level out almost towards the end. Now the position, if you were to integrate this function right here, it's going to kind of look like this. It's going to kind of go, it's going to start building up quickly because you're going to have that that high velocity at the beginning, but it's going to start to tamper off towards the end, and you're not really going to see a change in X because that's when the car's really essentially is going to be stopping about towards the end over here. And so this gives you sort of the so if you look towards the answers, you see that D and B are the only ones that have downward sloping velocities that kind of level off towards the end, towards later times. But for B, that positions is almost as if the car is going backwards, which that wouldn't make any sense. It can't really start forward and then go backwards. So then the only correct answer would be D. Alright, so question number 10. An object with an unknown initial velocity has a constant acceleration with components a of x equaling 8 meters per second squared and a of y equaling 0 meters per second squared. Which of the following is a possible expression for the position of this object in meters for both x and y directions as functions of time? So essentially here, we're just going to straight integrate each one of these two components to get down to their position and velocity, um, pos position and velocity functions. So the integral of a of x with respect to time is equal to 8x meters per second plus c. Why did I forget that? Plus c. Well, let's set that c1. The integral from a to y dt is just simply plus c because if you slap an x on the 0, it just becomes 0 and it cancels out. And it's just essentially a constant because it wouldn't be changing. So that would be c2. Um, so then these would be equal to the velocity vector. So that one with respect to x, this one with respect to y. Um, Now if you integrate, you have to integrate that further to get to the position vector. So for x, it would be the integral of v of t with respect to x dt, and that is going to be um 4x cubed plus c1x and then plus c3, adding another constant on there. And then for the y, it would be the same thing, but just with the y component of this velocity vector, and you're getting c2x plus c4. So we have some constants here that we need to rule out. So ultimately, you have to look at the functions that would fill these um, that would be plausible answers. So if we look at A, the x component for the function, well, we look at the x component first because this has to be cubic right here. So the only answers for that would be C, D, and E. Now C, they they did their integration wrong because um, the velocity needs to be integrated correctly. The velocity wasn't integrated properly, and they didn't divide by 2 when they did the reverse power rule. So it has to be either D or E. Now, so we look over to the Y because those constants clearly would have been 0, and that would have fit the equation. Now for E, it's either 8t or 4t cubed. Now there's no cubes here, it's only to the first power. So it has to be D. Alright, so here we have question 16. An object is pulled into a non-ideal spring, compressing the spring. The magnitude of the force F the spring exerts on the object as a function. The magnitude of the force F the spring exerts on the object as a function of the compression X is shown in the graph. Which of the following graphs best shows the potential energy of the object spring system as a function of X? So what we're essentially doing is pushing a spring in on itself. And what that's going to do is that's going to raise that potential energy or that U of X, or U of S, U of X. It's all the same. So essentially, it's going to be following the exact motion of this force because as the more you push as the more you compress the spring, the more force there's going to be. So we're going to look at upward sloping answers. So we have A is an upward sloping, C is upward sloping, and those are the only two. So since this potential energy is going to increase as much as your force is going to increase, it's going to be look more like the graph that is shown. So the graph shown sort of goes up sloping, sort of like an exponential. So the only answer that is an exponential is C, and that is the correct answer. All right, so here we have question 22. The magnitude of a force as a function of time can be represented by f of t is equal to r t squared minus s of t plus z. Um, and the direction of the force does not change. If the force is exerted on an object of mass m, the change in velocity of the object between t equals 0 and t equals t seconds is blank, and that's what we're trying to solve. So this force equals mass times acceleration. So we're trying to get to this acceleration graph. So this acceleration is equal to the force divided by the mass. So we are going to do this, and that will be equal to our acceleration. So the acceleration is equal to rt squared over m minus st over m plus z over m. So in order to find the change in velocity, you need to integrate this. So we're going to integrate this side, integrate that side, and you get this velocity. Right, we want the limits to be from 0 to t. So this velocity is equal to r over 3m t cubed minus st squared over 2m plus z over m t. And then you evaluate this from 0 to t, plugging in those t's for the first value on the top first, and then you subtract it by the one on the bottom. So that would be velocity would be equal to, or for the 0, it all cancels out, so you're fine there. So you really just have to plug in these tops. So it's r t cubed over 3m minus st squared over 2m plus zt over m. And that answer choice is answer choice D. All right, so question 30. A certain one-dimensional conservative force is given as a function of F by the expression F equals negative kx cubed, where F is in newtons and x is in meters. A possible potential energy function for U for this force is what? So what we do know is that this mechanical energy is going to stay constant. So it's best to think of it almost as 0. So that's going to be equal to that kinetic energy plus the potential energy. And we can find this potential energy, which is this U. This is really what we're finding. So we're essentially setting this equal to negative kinetic energy. Now we can see that we can find this change in energy because the integral change in energy is equal to the integral of this f vector with respect to t. Then we have this function up here, so we can find that by integrating this. So it is negative kx to the 4th over 4. So then we plug this back into this equation up here. We plug it back into that equation up there, and we get u is equal to kx to the 4th over 4 plus c. I almost forgot about that. And that gets you that answer D, which again is the answer.